Well, thank you all for joining us this morning. This is certainly a topic, or at least a title, you've heard a lot about in the last 24 hours. If you've been at VertiXchange, people kept referencing the duck curve, right? And what are we going to do about the duck curve? So really what we wanted to do in this panel, we've historically had panels on energy storage, but we wanted to be a little more specific here about the applicability, hence the title, Shooting the Duck, right? How do we ultimately use energy storage as a way of dealing with this fundamental problem? Now, if you think about it, energy storage, if you've seen the little thing I wrote, it isn't new. It was actually first developed in 1800. Anybody know who developed it? A guy named Volta. Volta. Volta developed the first battery stack in the year 1800. We've had battery storage for a very long time, but we've also had other forms of storage. All of you who are familiar with pump storage hydroelectric, that's been in place for since 1880, I think, around the world, first in Switzerland and Italy, and then in the US in the 1910s and 20s. And pump storage hydro, despite everything that's happening in the world of batteries, still accounts for 96% of all the energy storage on the planet Earth. The other 4% is batteries and everything else, flywheels, other gravity-based storage. So we've had storage for a long time. What's different now is the way we're using storage, simply because we didn't have vast amounts of renewable power in those past years. Now with renewable power, we have this fundamental mismatch at times between supply and demand, right? One of the things that's special about the electric utility industry, I've said this for at least 40 years, I said we're one of the only kinds of businesses in the world that manufacture the product just for you when you ask for it. Because we had no effective way really to store it and then give it to you. So when you turned on your light, I made those electrons just for you, right? Made to order. Now with this fundamental mismatch between supply and demand because of renewable power that works wonderfully with one problem: it's controlled by Mother Nature, not by man. So the wind blows or it doesn't, cloud cover comes in, gray days, rainy days, and suddenly we have this dramatic variation. One of the biggest problems we're facing in California and the western US right now is overgeneration, hence the duck curve, where the easiest example, which we've had for several years, is the wind blows like crazy in the middle of the night when you're all asleep and nobody's using power. So we end up paying people to take power. It's kind of a crazy thought, right? We're paying you to please take the power. Well, obviously, a much more satisfactory solution is to store that power and use it the next afternoon when we have a peak and not have to turn on a fossil fuel plant and be able to ride through it with the stored energy. So this whole notion of how we shoot the duck, how we make supply and demand match in real time, because you're impatient people. When you flip the switch, you won't wait 4 or 5 minutes, right? You want the light to come on now. So how do we match supply and demand in real time using energy storage as the vehicle to make that happen? And we're going to talk about that with an awesome panel here. Let me introduce our panelists real quickly, starting at your far right. We have Ruben Dagstanian, who is the Executive Vice President and CTO of Tabuchi Electric. Ruben is an electrical engineer. He's got a long history in our business, and he'll tell you a little bit more about that. And then next to Ruben, we have Eric Takayasu. I've known Eric since he was in short pants, I think. Eric is both a remarkably capable engineer for Southern California Edison, Director of Electric System Planning and Grid Modernization. He's the guy who's got to make that all happen on the electric grid for Edison. So he's a very capable engineer. He also is one of those unique engineers who's good with people. I can say that because I am one. I used to tell people I became an engineer because I didn't have a good enough personality to become an accountant, right? So Eric's got the whole package. He's fantastic. Sitting next to Eric is Erica He, who we have had a few, or no, pardon me, Carl was sitting back. I messed up. I'm not going to do Erica yet, I'll do Carl. Carl Stills, who's Vice President of Storage Integration for 8 Minute Energy. And Carl, I first met in his many years with Imperial Irrigation District. He was really the energy manager for the 6th largest utility in California, Imperial Irrigation District. And since then, he's gone on to work on energy storage development and integration, most recently with 8 Minute Energy. So we welcome you. And now I can go to Erica. Erica has joined us 3 or 4 years, I think, right, at VertXchange. She's a senior advisor at the energy storage or energy subsidiary of Sumitomo Electric. She's had a number of roles. She leads North American market development for Sumitomo Electric's Smart Energy Solutions business, and she is also an engineer from Columbia University. And then we go to Lars, and Lars is, I think, your first VertXchange on a panel, right?
First time.
Yep, so welcome. Chief Technology Officer at STEM. And you've all heard of STEM if you play in the energy space. So he's the chief technology guy. He's also an engineer from Stanford. So couldn't get into SC, huh?
I couldn't.
Oh, man. Okay. But he's a mechanical engineer. You know the old rule, right? Mechanical engineers build bombs, civil engineers build targets. Anyway.
What does that have to do with energy storage?
Nothing whatsoever. But that's why I get to be moderator. Anyway, Lars has got a long history at Siemens and other prior gigs where he's worked on a ton of stuff related to basically sort of smarter grids and smarter approaches to the technology of managing the grid. So with that, each of our panelists is going to give you just a little view, sort of a perspective on this issue of shooting the duck and storing renewable electrons coming from where they are in their individual businesses or enterprises. So, Ruben, you want to start us?
Yeah, thank you. So at Tabuchi Electric, we view this problem as you articulated it. Is this better?
Yes.
Yep. It's my first time too. So we're viewing this as a necessity as far as storage. As you all pretty much already know, that renewable energy implementation has caused this problem. In California, it's called duck curve. In Hawaii, it's called Nessie curve, I'm told, because it's much more severe. Its impact is much more severe. So the storage itself is a necessity to be able to implement adequate amount of storage and make sure that the grid doesn't go completely, out of control. So with that said, we have looked into this from a standpoint of how do we make our inverters with storage so that it can solve, or at least it can be part of that solution. And it's been interesting to see the results. We have implemented quite substantial amount of our solutions in Hawaii specifically, and in Toronto area as well. And interestingly, the data are very, very encouraging. Now, with that said, it's great. The concept is great. We know it is a necessity, but unfortunately, today's technology, storage technology, is such that it is a game between performance and cost. So, and safety, right? A lithium-ion is today's best technology available at somewhat mass scale. And we all know that lithium-ion technology has a little issue. If you want to make it safe, then you can't really squeeze out the performance that would be desirable, and vice versa. If you want to get the performance that you desire, then safety gets compromised. Obviously, the verdict at the end of the day is better safety. Therefore, we don't get the performance as much as it would be desired. So that's the area that we're working on, both on residential scale and on commercial scale as well. I represent Tabuchi Electric. It's a Japanese company. In Japan, we have both solutions. In North America, we have brought in the residential solution to collect data first and see how this pans out. And the data is very encouraging. And we're working on commercial solution as well, implementing commercial solution as well. So.
Great. Well, thank you, Ruben. We're going to have some questions later about a couple things you said that got my curiosity up. Eric, you've got the task of somehow taking all this stuff that all these bright people are inventing and figuring out how to integrate it all into a grid and keep the lights on, because ultimately, no matter what they invent and how cool it is, when the lights go out, you're the one who gets in trouble, right? So tell us about that journey.
So all I got to say is, you know, when you know Jim a long time, he puts no pressure on you whenever you're going to give a talk. None whatsoever. Anyhow, first of all, it's a pleasure to be here. Good morning, everyone. So Southern California Edison, just a little bit about the company. We are one of the largest investor-owned utilities in the country. Our population that we serve is about 15 million people. We serve about 23 gigawatts of peak demand, and there's a lot within that in terms of the renewable resources and where we are today with that. 40% of our energy today comes from carbon-free resources. So when we think about this issue of the duck curve, it really is a composition, as I think as Jim eloquently stated. It's really based on the amount of solar that we see on the system today. And it really is a cost-effective resource. And when we look ahead, it really is about what do we need to do in order to get to our greenhouse gas emission goals here in the state of California. So we are moving from 2020, getting to where we are at 1919 levels of GHG emissions and getting to 40% below 1990 by 2030. And that's only 12 years away. So if you start off with looking at what is required there on the electric power sector, it really represents about 19% of the emissions in California. So the clear conclusion there is we're going to see a lot more renewables. We think that the 50% renewable portfolio standard is really the starting point. Probably needs to get closer to about 70%, and if you count hydro, it gets to about 80% with distributed renewables. So this is going to provide an interesting challenge when we think about what the future of the duck is going to look like. And I have a really good friend who works in Arizona Public Service, and so the joke that we have right now is, he says, boy, our business model looks really great because you're always providing better than free power to us. Well, that's really good. So you can put that into your portfolio. So really, I think the way to look at this is there's really kind of a supply side issues that we have to deal with, and I think we also have to look at this from the demand side. So on the supply side and the resource diversity in the portfolio, if we do continue down the path of where we are today, we are going to need things like storage in order to complement the renewable resource portfolio, both from an intermittency perspective, as well as to deal with this issue of overgeneration. I mean, it really presents a prime opportunity here to look at it from a supply side. But then the question becomes is, how does the demand side impact this? So we also see, in terms of meeting our greenhouse gas reduction goals, transportation is one of the largest sectors, is the largest sector in that whole pie of what contributes to GHG, about 39%. Now, when we think about needing millions of more vehicles on the road by 2030 to the tune of about 7 million, along with goods movement and poor electrification, that also provides an opportunity for us to think about how does that influence the shape of the duck curve. So I do think from a technological view, there are some things that we need to think about in terms of options. I mean, either you store it somehow, or you export it, or you do a little bit of both. So I think this is really where I would be very interested in a lot of conversations here about how we can do this. When I think about it from really a planning perspective, citing the resources, getting that diversity, and lowering the cost for our customers to minimize the amount of investment that's needed on the transmission system, I think is going to be key. I think if we can get to a place where there is more resource diversity, it does lower the need for as much storage, but we know we need it. So the question becomes is how do we manage the amounts that we have? And at the end of the day, we want to see benefits to our customers. So I'm very interested in technology. Jim, you mentioned real-time, matching supply and demand. So when you think about supply side and demand side, I do think there's going to be a question of where does that occur and how is that coordinated across the distribution and the transmission system. So there's a lot of activities today around things like distributed energy resource management systems. What role do they play? How could they help manage power flows and model congestion, both from the distribution and then looking up towards the transmission? But one of the key things here is there's no visibility that the independent system operator has today to all the resources on the distribution. So we are working today between the IOUs and our ISO to really think about what this coordination looks like. There's both a coordination, both from a planning perspective as well as an operating perspective. And I do think in the future, this is going to change the technology in our control rooms, the technology in our grid operation centers, the types of systems that are needed in order to manage reliability both on the transmission and distribution. So with that, I think I'll pause there and move over to the next speaker. Thank you.
Great. Thank you, Eric. So, Carl, 8-Minute Energy is doing some really cool stuff in this particular area. Tell us about it.
Actually, 8-Minute Energy is the second largest solar developer in the United States, and we're the largest independently owned utility scale solar developer in the United States. We do storage and solar. We're presently starting construction on a 250 megawatt AC solar field down in Imperial Valley that we're selling to these guys. So, and we've got another 115 megawatt DC, 90 megawatt AC out in Kern County that we're selling to a public agency. We've got a huge pipeline of both solar and storage. I can't talk about some of the storage because we're in negotiations on some of them. But we generally work in 50 megawatts and above, so we're a large utility scale group. I'm actually an ex-energy manager of IID. I've actually put in a 20 megawatt hour storage facility. I'm the guy that it was the largest in the United States at the time that it went in, but it's starting to be exceeded now. But what I saw as the energy manager was the fact that storage is absolutely going to be needed, the variability that goes on your transmission system, and I think Eric alluded to that, the NERC requirements that are out there, the issue of the duct curve, and I want to say, before I say that, how many of you are familiar with the duct curve? So some of you aren't, so I'll just real quickly say a duct curve is generation load curve. You know, as you get up in the morning, your generators ramp up, and then as you get to like 7 o'clock, your solar starts coming up and your generators have to ramp down. And there's a real trick to operating that. And then after your solar comes up, it levels off, and about 4 to 5 o'clock, it starts coming down. Your generators now have to ramp back up, but your load's grown, so you've got some really high ramps up there. And then at the end of about 7, 8 o'clock, the load starts coming down the generation. So looking at a load curve like that and trying to figure out how to mix and match the generation from an operational standpoint is a huge issue. The Cal ISO's duct curve right now for 33% renewable by 2020 is projected to be on that last ramp, which is a critical one, about 13,000 megawatts over a 3-hour period of time. And the other one coming down when you're taking off generation and ramping up, you're looking at flattening out the duct, so you're going to have maybe some overgeneration issues. You don't want to do that. You want to try to balance that load, as Eric talked about. But that's going to create some real unique challenges, especially I'm going to focus on that last one, because right now from the Cal ISO standpoint, you're looking at 13,000 megawatt ramp. But there are other balancing authorities out there. And as we transition to SB 100, and we had dinner with Senator Skinner about a month ago, and she believes they have the votes to pass SB 100, which is 100% renewable this year. As we transition towards that, it's going to cause utilities to accelerate and go to 50% by 2025, which means you're going to have more renewables in the next 10 years than are presently planned. There'll be solar, and again, you're going to increase those ramps. We're hearing the Cal ISO, we're hearing numbers like 17 to 20,000 megawatts. Your other balancing authorities are going to have another 4,000 to 5,000 megawatts that they're going to increase. So you're looking at somewhere between 20 and 25,000 megawatts. Right now you have an overabundance of energy, but will you have an overabundance in 10 years? This is going to change from a supply side to a demand side curve, which means that in that 3-hour window, when you're really looking for those ramps in that generation, if you don't do something now, you're going to pay a premium price. It's supply and demand. Demand goes up, price goes up. So you've got to do things now to make it affordable. And what you can do is use storage in the process. And what's good about that is storage right now is economically viable. It will compete against gas peakers. It will compete against the variable cost of gas peakers. So solar and storage right now coupled together is very pricey and very affordable and can actually make a difference, because what you can do is energy arbitrage. You take energy at a cheaper price and you shift it to that time frame when that cost is going to be up. I've talked to marketing people right now. In the summertime, when the energy is at a premium, those markets in that 3-hour window are between $75 and $1,000 if you're going to the eastern markets, and between $75 and $200 on the Cal ISO markets. In the wintertime, it's all about $75 to $200. Think about the price and that demand curve for that 3-hour period, how much cheaper you can take under probably $50, somewhere between $30 and $50 with solar plus storage, depending on the mix, and put that in something that's 75 to 100. Your gas turbines, if you have gas turbines and you're trying to displace them, probably range, if you use a spark spread methodology. A GT might have a 9,000 MMBTU efficiency rating with $3 gas, about 27 bucks. Start adding your variable O&M cost, your environmental cost, your start-stop cost over that 3-hour window, you're going to be between 60 and 75 bucks. You're still underneath that. So not only does it make sense to mitigate that curve, it makes sense to mitigate it because it's economically viable and you can actually lower your cost with the benefits you get from solar and storage.
All right, thank you, Carl. Now, Erica, you're in the position, your company is making the product that they're all talking about using, right? Some variation on electrochemical solutions. A lot has happened in the last 5 years even in terms of price and performance. Tell us a little more.
Okay, thank you. So it's great that I speak right after Eric and Carl, because they throw out the issues they're trying to solve and the projects they're trying to develop to solve these issues. And I come from a company called Sumitomo Electric. So I'll share a little bit more about our position, why I'm here today, and how we can help to solve the issues. So since Carl just asked a great question about how many people are familiar with dark curve, so that was great. So I know that almost everyone here knows about dark curve. I just thought about a better way to introduce Sumitomo, because most people have not heard about Sumitomo, the name, but we're actually a very large Japanese corporation operating in 350 different countries. Since you're all familiar with dark curve, I can say all the products that you know that cause the dark curve, from the solar generation, from all the cars, the lightings, all the water, everything that caused the dark curve to occur, there's a product that using Sumitomo's solution or material or components in it. So Sumitomo is a very large global corporation that we provide raw materials, products, semiconductors, solutions, systems, from power generation, transmission, to info communication, networking, infrastructure controls, to automotives, wirings. So basically, anything that you use in your daily life, you're probably using a Sumitomo product. So thank you all for easing our supporting our business. And because our wide variety of products and business that cause the potential dark curve, we're here to solve the problem. So Sumitomo has been around for 120 years and providing solutions to all the different industries that I've just mentioned for 120 years. And utility business has always been our genes. Why? Because 400 years ago, the Sumitomo family started the business by copper mining. So you can imagine anything that's related to copper mining, that's the Sumitomo's core business. So for our utility energy business, our core foundation has been providing power cable and all related solutions to the energy industry globally. And so that's why Sumitomo take our pride in providing reliable, safe solutions to the energy infrastructures, to the utilities in the world. And with that said, now we're back to the energy storage. So what we are trying to do, how can we support, how can we help all the guys here to solve the problems with the dark curve? Sumitomo has been involved in energy storage technology development back in the 80s because our deep roots working with the utilities in supporting the utility industry. And just like Jim mentioned, we've been developing something, a kind of a different variety from the majority of the mainstream technologies that everyone's familiar with. So right now, when we talk about energy storage, there are basically two different types of technologies. None of them are new. Like Jim just mentioned, energy storage is not new. It's just people are finding new ways to use the technologies that's been available. Lithium-ion batteries has been around for years and years. And there's another type of technology called flow battery, which has also been around for different years, just that people has never used it for this kind of applications. And so Sumitomo has been devoting our development efforts in developing this type of flow battery using vanadium electrolyte liquid to realize the charge and discharge. So it's a slightly different type of technology variety from the mainstream lithium ions, but we've been using this at utility scale at different industries globally, supporting the utility distribution and transmission operations since the 1980s. Most recent project that we've done is in California. It's right now operated by San Diego Gas and Electric. It's been operating since June last year. It's right on San Diego Gas and Electric's major substation, connected to their distribution feeder line, supporting their daily operation for their distribution line. And it will be connected to CAISO's interconnection from July this year, and it will be realizing the dual-use application supporting both the utility distribution operation for daily operations and as well as connecting to the CAISO wholesale market. So these are the solutions we're bringing to California to support the dark curve.
Thank you. And last but not least, we want to hear from Lars, because STEM is doing some pretty wild stuff with artificial intelligence and virtual power plants, and I don't understand all of it, but I stand in awe when I read some of the announcements. So tell us more about that, Lars.
Wow, so it's all very imaginary. No, so I think I can play off of everything these guys have already said. In fact, we're partners with companies like Sumitomo and Tabuchi, and we work closely with Southern California Edison on virtual power plant services. But I think maybe a little different take on how some of the storage can be deployed and operated. Our business is about enabling storage deployment at customer sites. And storage is really one of the first elements of flexible energy resources that can be distributed to customer sites, and where the customer can actually benefit as the host of that facility. So our customers are typically saving money through demand charge savings and other savings they can get through energy arbitrage or shifting products, integrating with solar plus storage, and then using that facility to benefit the customer also affords us the opportunity to benefit the grid through aggregations. So we will aggregate dozens or hundreds of small sites relative to some of the big sites you've heard about into a virtual power plant. And today we have over 200 megawatts under contract, 85 megawatt contract with Southern California Edison for virtual power services. We operate in about 8 different utility territories today, and are following the same sort of practice where we see this mission of deploying the world's largest connected energy storage network and being able to provide both benefits for the customer members of that network as well as the hosts of the grid side. And one of the key things about that is while today we're talking about the duck curve, pretty soon we'll be talking about that EV curve or something that's going to be renamed because of the shape will change. And then we'll also be talking about things like distributed resource planning processes that look at the locational value of DER, and now we're talking about locational capacity constraints, right, and optimizing that infrastructure, and in fact hardening that infrastructure through distributed resources. All of those will effectively change the character of what I would call behind the meter grids. That is, how do consumers actually participate in that process? How do they adopt the technologies, which include storage, but also include small-scale generation, certainly PV, and how will all that be integrated into a system that can take advantage of those changes as they come down? I mean, there will be combinations of market offers, participation in wholesale markets, new rates and tariffs that reflect a cost of service or a value of distributed storage or distributed resources generally. And we see the opportunity to help balance the behind-the-meter grid with storage to help it better participate more flexibly in that larger scale change that's going on across the distribution grid. Now, to do all that requires software, requires intelligence. And so while we work with energy storage, we don't actually manufacture energy storage products. We integrate them with our network. We onboard them in a process where we can say very carefully, this is how that product will benefit the customer and how we can dispatch it in the grid. And then we operate it remotely through a monitored service and provide that operation in the cloud as well as with a local control system that help to co-optimize that asset over the course of its life. And we do that through the artificial intelligence, the machine learning, and processing lots of data about what's going on both at the site as well as on the grid in order to achieve those results.
Cool. Awesome. Thank you. Well, here's an interesting contrast if you think about it. You have Ruben and Erica who are going to supply all these different kinds of applications. But you have Carl, who I view as a supply side guy. He builds utility scale, which to me is a supply side asset, right? Lars does really what I'd call almost demand management. Right? He's on the demand side most of the time with his applications. Eric, is it easier for you to manage this grid design with behind the meter demand side applications for energy storage or for utility scale supply side applications?
Again, no pressure, Jim.
Yeah. If you could solve that, we pretty much all have gotten what we paid for here today.
So I do think that in terms of where a lot of our directed efforts are today, I mean, we do recognize that the transmission system is going to continue to expand with large-scale renewables. But I think the point that Lars is making is on the distribution side. There is a runway there of opportunity that is really we're working towards trying to build upon, because the distribution system, when you think about where it's about customer choice, it's about the flexibility of customers being able to use their technology choices to benefit themselves as well as the grid. That in of itself connects things like our distribution resource plan proceeding, where we are trying to understand and calculate and determine and actually share where there's grid benefits associated with this. I think where the hardening and the technology developments are occurring here is on the one hand, that's really kind of a planning effort to be able to understand, model, display information, work with clients like STEM on efforts like that. But there's also a systems view of this in terms of, how do you realize those benefits locationally? And that is about dispatch. It is about understanding the profile of those resources as well as the low profile of our circuits and our substations. And getting to a place where we can dispatch those resources in a way that realize those benefits at the time and location in which it's needed. There's seasonal variations, there's time variations, there's frankly variations in customer behavior when it comes to loads, especially when we start talking about mobile loads in terms of electric vehicles. So I think that is a place of not really is one more important than the other between transmission and distribution. I think the question here is how do you coordinate across both of them? Because you have reliability issues that exist in two dimensions. You may not have full coincidence between the reliability issues on the transmission as you will on distribution. So the interesting thing about the customer resources is with that coordination, you can really figure out the optimal solution to really try to solve both issues, but they really can't be looked at each separately in isolation.
You notice how he kind of danced all the way around that answer? I told you he was good, didn't I? No. Ruben, you said something that I had to take a note, and it's something we tend to forget when we're talking about AI and Internet of Things and integration and circuitry, and it's all cool, but we're still dealing with a product that can kill people, right? I mean, it's a dangerous product if not properly managed. And you said something about I couldn't optimize the performance and maintain the safety that I needed, so I had to pick safety. What do you mean? What was the problem?
Well, you just said it yourself. You cannot kill people, right? So the technology is there, at least as we know today, lithium-ion technology. But if you noticed, every time it is left unattended, whether you're traveling on an airplane or whatever, they make you take it out so that it doesn't go out of control. So with that said, there is quite a bit of work in the industry, whether it is solid-state batteries or some other technology that is coming up. So far, price-wise, it's not really working out. But every new technology comes up with high price, and then as it gets more and more room in the marketplace, it starts going down. Today, what we have the best, as we know, or at least as I know, is lithium-ion technology. But as far as performance goes, well, it's just a human nature, right? More is better. Always more is better. So when you're trying to squeeze out more, then you have to deal with safety issue. You can't just push all the way through and then have a problem on your hand. I mean, fortunately, we've had much smaller scale problems with lithium-ion technology. If you remember the cell phone batteries and stuff, until they sorted out what to do and how to do. And for larger scale, that does have a potential of making a disaster out of itself. So that's
important for us to always keep in mind that we can't ever let that safety component sort of leave our consciousness as we're talking about this technology, because ultimately that's our primary responsibility, right? Yeah, every utility guy, and 2 or 3 of you have been utility guys or are now, we learn first is safety, right? Then compliance, then reliability, then cost. Backwards compared to a lot of businesses, but it's the way we've got to do it from the responsibility we have to the public. So folks, we have a few minutes left, and we'd like to get some questions here. I've got, okay, you're number one, go.
So question for Eric and Jim. So right now we're 70, 80% renewables. Has Edison done the modeling to see what that means to the system, and you know, what is that duck curve turn into a boost curve, something more unmanageable?
So that's a great question, and so we have done some modeling. One of the things that I'd like to sort of point to, and it's available outside there, is our white paper on the clean power pathway. The modeling there is looking at a 70% RPS scenario. And what we look at is things like intermittency and issues with overgeneration. And the modeling suggests that you need probably about 10 gigawatts of storage if you're going to have 30 gigawatts of renewable resources. So this is an interesting issue because when I go back to if the overgeneration issue comes, such that we have significant reliability issues, there's really a few options there, right? One is to store it using that type of magnitude of storage. The other is to export it, but that's going to require regional coordination in order to accomplish that. And I think the thing that we probably want to avoid, if possible, is curtailment, because that essentially, we're not able to use the energy that we want to use. So I would say that it's hard to really forecast, though, what the real curve is going to look like. That's really kind of a supply-side analysis, but I really think that the key here is what do we do on the demand side. So I think as programs, the long-term trajectory here is to encourage charging during the middle of the day. So we're starting off with time of use rates, but to the extent that we could get this to be a little bit tighter, a little bit more regionally and locationally coordinated, then I think that's when this new shape will start to take form.
Can I jump on that, because that's exactly what that's exactly what I was going. We have the opportunity with storage to shape load, right? And I think that's where the programs that are being put out, the shifts in the time of use rates recently, this is all helping to sort of try to drive to shaping load. I think we have to do a lot more, and we have to do it now with the eye towards storage, being more ubiquitous resource. And doing that, we'll be able to pretty dramatically shape load in order to be part of that solution.
But if I may jump in as well, but also the nowadays requirements like 1741 SA, making inverters smart inverters, so to speak, that also provides a necessary interface to be able to control each DER in its place at a massive scale through the utilities or operators.
I think there's another dynamic that really needs to be looked at, and as you go more static, you're going to have a loss of inertia on your system. That rotating machinery is being displaced, and that creates an issue on your system of reliability of being able to sustain that system under a fault condition. So I think WEC right now is, the Western Electric Coordinating Council, is doing a study to look and see what that minimum amount of rotating machinery is so you can get inertia on your system. Storage can provide synthetic inertia, and it's very fast ramping. It can discharge into a circuit really quickly, but you're still going to have some type of inertia to get that torque on that system to keep that up. And it's a huge issue. It needs to be looked at. I think that it is being addressed, but again, the model is completely changing, but we have to stay within requisites of a reliable system.
You rarely hear it mentioned, but inertia is something that keeps all us engineers up at night. It really is. Steve, I think you were next.
Today, we have one grid, essentially. We have a handful of system planners. But as community choice just takes off at a rapid pace, are we going to end up with 400 system planners? And how are you going to tackle that group?
Okay. I think that kind of took care of that issue, Steve.
My understanding was the CCAs were not the grid operators in most cases, so that the same folks who operate the grid today have to deal with the fact they have a new retail supplier managing customers on those grids.
Yeah, but I'm thinking you're going to have people competing for the transmission lines and buy the commodity. Just curious.
That would be absolutely right.
There's a bigger issue here, and that's, you look at the load profile. Typically in California, your load profiles are all the same for your various utilities here. At IID, we had a load profile that was very heavy summer load, over a gigawatt in the summer, but only 350 megawatts in the winter. Okay, so what happens in the wintertime, your load drops down. Now, the more we go to a static must-take contract, the more you're going to be long in the wintertime, and that long in that wintertime is going to be an issue of overgeneration. You're going to have regionalization or something to that effect, or regional cooperation, so that you can reach a larger market to be able to sell that energy out. Or you're going to be paying for it twice. You're going to pay for it to buy it, you're going to pay for it to curtail it. So to keep that cost down, there has to be cooperation among balancing authorities.
I can only take one more because of time, but then you can speak to, and you were next, then you can speak to the panelists afterwards and get a cup of coffee, okay? Go ahead.
So does the electrification of the transportation sector create a monster duct when people go home and plug in their cars just when solar goes down and when the wind comes up? Or is electrification of everything going to kill the duct? Is it going to be roadkill?
Actually, it's going to complicate matters, because one of the local utilities actually did a study back when De Leon did his 50-50-50 rule to have 50% electrification on the grid. And I think the 5 largest utilities were mostly involved in that study. And it basically said if you put like 500,000 electric vehicles on there, the utility was looking at it, not only would they have an EV and get the emitters off the road, but their load would double because of the charging at night, and their power factor would increase from about 48% to about 65%. So you're going to have more load with electrification. You're going to be charging, and then you'll be able to use those batteries at night for storage.
And I charge my car starting at midnight. I think we're going to see more, no, seriously, we're going to see more load shaping products that say these are times to charge because it's either free during the middle of the day, or you're waiting until some period of time when you've got some diversity in the network.
And I'll also say that I think that we are reaching a point of both loads and resources being, a lot of inverter-based devices, a lot of different variations in those devices. And so if our distribution systems don't evolve to be able to handle that kind of complexity, then I do think we reach a place where, maybe it does take, I don't know how many planners and other folks that are needed to do that, but getting better intelligence, better information, interacting with those devices to inform our planning and operations, I think is how we evolve the system going forward.
Wonderful. Folks, please carry on the discussion after this. Look these folks up. They love to talk about what they do. Would you join me in thanking our panel?